Hello everyone, thanks for watching our video on finding the optimal solution to the Yinsh game. In this video, we will analyze and demonstrate 5 different planning models in terms of design principles, strengths, and weakness, and talk about the challenges and solutions we encountered during the design process. We have implemented a total of 3 blind search algorithms as baselines, including BFS, DFS, and iterative depending. However, since their research is blind, the performance is not good. So we first try a model-based planning, which is value iterations.
Our initial attempt was to implement a value iteration method, but later realized that there's actually no model for the Yinsh game. So we decided to attempt it with manually set probabilities to see how the performance go. And one of the challenges that we faced was how do we actually decide the value of the probabilities. And this model-based method could be improved by applying online learning, which will lead us to the next method. Compared to value iteration, we implemented a multi-arm bandit algorithm in Q-learning to decide which state action pair to take during the training of the transition probabilities. The biggest challenge that we face is that it's very unlikely to reach global optimum policies because of the 1 second think time limit that's given in the project, as all online learnings are really time consuming.
Additionally, we implemented Monte Carlo tree search. The benefits of it over blind search and value iteration are MCTS does not search all the states, but focus on the search that relates to the goal. By simulating as many as different states, the optimal solution can be found. But in order to find the optimal solution, the first challenging we have to solve is how to visit more nodes in a limited time. We combine selection and expansion together. We ignore the process of checking whether the node is fully expanded, but directly find a leaf node to start the simulation process. By doing the experiment, the algorithm can simulate up to 250 different states in 1 second. However, this algorithm has limitations. We use greedy E technique to allow the agent to have opportunity to search paths that have not explored before, and the random selected action may result in a serious consequence. That is, it may result in a scoring points for the opponent. For instance, in this case, the green ring moves from point A to point B, resulting in allowing the opponent to score. This model can be improved by designing more reasonable heuristic functions.
Since the above planning models didn't perform too well, so we tried heuristic searches to express the value of the actions more accurately. And we designed the heuristic function in 2 stages, placing and moving stage. In placing stage, the function prioritizes placing rings at intersections with more potential choices. And in moving stage, the function considers 3 main factors. First factor implies that more counters means that there's a better chance for the player to win. Second factor counts the number of 3 or 4 or 5 counters in a row. Last but not least, the third factor makes sure that whenever there's a chance of scoring, the agent takes it for granted. We added this heuristic to the weighted A-star algorithm, and the effect was significantly improved. But due to the limitations of the single agent policy, it was not powerful enough for the competition, so we eventually tried to further optimize this single agent policy into a multi-agent policy.
The last is our final agent, custom minimax. For the original version doesn't perform well with time constraint theory. We improved this problem by computing the heuristic in real time at each layer and maintaining it with a priority queue. As minimax is based on multi-agent policy, it shows the strongest performance among our models. Here are 2 demos showing the uniquely strong performance of minimax in 2 stages. First, in the placing stage, minimax tends to restrict opponent's mobility, and in moving stage, minimax will stop the opponent from getting rewards with minimal cost. In this state, minimax has 2 available actions. The agent will choose 2 because action 1 loses 2 of our own counters.
That's the end of our presentation. Thanks for your time.